In this section of the equilibrium unit, we're going to look at interpreting K, the equilibrium constant. What does the value of K mean? Remember that K is a ratio of the concentrations or partial pressures of the products to the reactants. So if K is much, much larger than 1, the reaction is product favored. In other words, at equilibrium, the product predominates. If K is much, much less than 1, that means the reaction is reactant favored, or reactants predominate at equilibrium. And just, as a reminder here, K is equal to the ratio of the concentration of products to reactants. So if the products are much, much larger, and we're dividing that by a smaller number, then we'll get a K that's much larger than 1. If, on the other hand, the reactants are much larger, we're dividing by a much larger number, we'll get a K then that is much, much less than 1. So that's mathematically how this conceptually is working. Sometimes a reaction is reactant favored, and sometimes a reaction is product favored at equilibrium. So what does the value of K mean? K determines the spontaneity of a reaction. Spontaneity refers to a process which continues forward without any input of energy. A spontaneous reaction or process will produce product without the need to supply energy to the reactants. Let me just give you a really simple example of a spontaneous process. Ice that is sitting on your counter will spontaneously melt at room temperature. But that same water will not spontaneously boil at room temperature with no additional input or need to supply energy to the reactant or to the water in that case. Reactions with large equilibrium constants, K greater than 1, are spontaneous. And why is that? Of course, remember K greater than 1 is product dominant at equilibrium. So if the products dominate at equilibrium, that's a process that can happen spontaneously. Reactions with small equilibrium constants, those that are less than 1 or reactant dominant, are not spontaneous. Calculating equilibrium constant. The favorability of a reaction can be determined by examining the equilibrium constant. We have a reaction shown where 2 moles of H2O gas produce 2 moles of hydrogen gas and 1 mole of oxygen gas. And we can see this is a reversible process. The values in the table represent the concentrations of each species at T equals 0 minutes, T equals 5 minutes, and T equals 10 minutes. And we can see that equilibrium is reached when the concentrations have stopped changing. Okay. So those are our equilibrium concentrations. 4 moles of the molarity or the concentration of the water is 4 moles per liter. The hydrogen 6 and the oxygen 3. Okay. So I've written the equilibrium constant expression. K equals the concentration of the product, H2 squared, times the concentration of O2, divided by the concentration of water, squared. I've just substituted the values. So 6 squared times 3, divided by the concentration of the water is 4 squared. We get a value of 6.75. Since K is greater than 1, that means the products predominate and the reaction is considered product favored. If K was less than 1, the reaction would be deemed relatively unfavorable and it would be reactant favored. Direction of reaction. The direction from which equilibrium is achieved doesn't matter. The relative initial concentrations of reactants and products is not relevant. It doesn't matter if we start with more products or more reactants. It's only a convention that we calculate K by dividing the concentrations of products over reactants, since the reaction proceeds both ways. Unless specified, read the equation from left to right, where left is reactants and right is products. This convention makes it easy to understand the meaning of K. The equilibrium constant for a reaction is specific to how the reaction is written. If a reaction is reversed, the new K value will be the inverse of the original K value. Here's an example. We have calcium carbonate solid decomposing into calcium ions and carbonate ions. We have a K value of 6 times 10 to the minus 9. If I reverse the reaction so that I have the ions as reactants and the solid as the product, the K value is now 2 times 10 to the minus 8, which is the same as 1 over 6 times 10 to the minus 9. This makes intuitive sense, right? We have a value that's much, much less than 1, and a value here that's much, much greater than 1. If a reaction is favored in one direction, if the products are favored in one reaction, if I then flip the reaction, once it's flipped, wouldn't then the reactants be favored? So if it's favored in one direction, it will be unfavorable in the reverse direction. So in this case, this is the favorable direction. Okay, in this case, the product predominates. It's much greater than 1. If I flip it, it's now favorable in this direction where this reactant is favorable. So we have a K value much, much less than 1. Equilibrium constant and equation. The equilibrium constant for a reaction is specific to how the reaction is written. If the coefficients of a reaction are changed, the exponents of each substance will change in the expression, thereby exponentially changing K. Let's look at an example. This is the same reaction from the previous slide. The dissolution of calcium carbonate solid, and this forward reaction has a K equal to 6 times 10 to the minus 9. If I change each of these 1 coefficients to 1/2, what is the effect on K? We have K1. Okay, K1 here. So remember when we write an equilibrium expression, we only include aqueous or gases, not solids or liquids. So it equals the concentration of, in this case, the product Ca2 plus to the 1/2 power times CO3 2 minus to the 1/2 power, okay, which if I simplified is this product to the 1/2 power. And so the new equilibrium constant that we're calling K1 is equal to the original K to the 1/2 power. This right here is the original equilibrium expression for this reaction, okay, or this process. Okay. So we can take our original K, 6 times 10 to the minus 9, raise it to the 1/2 power, or take the square root is what that means. And we get 8 times 10 to the minus 5. Equilibrium constant multi-step reactions. Many reactions occur as a series of steps. Consider the production of AgNH3 2+ right here. There are 2 steps. First, we take silver chloride solid and dissolve it into its ions, silver plus and chloride minus. There's a K value for that, which we'll call K1, 1.8 times 10 to the minus 10. The second step then is to take the silver ions in and add aqueous NH3, 2 moles of NH3, and we get this AgNH3 2+ complex ion. We're going to call that the equilibrium constant for this step, K2, is 1.6 times 10 to the minus 8. The overall reaction is the sum of these two steps, okay? Where I've removed anything that is both produced and consumed, okay? So we have AgCl solid plus 2NH3 as my reactants, and then Cl minus and our complex AgNH3 2 plus as our products, okay? If the reactions are added together, so if I'm adding step 1 and step 2, equilibrium constants are multiplied. So the overall equilibrium constant for this multi-step reaction is just the product of K1 and K2. 1.8 times 10 to the minus 10 times 1.6 times 10 to the minus 8, or to the positive 8, which is 0.028. Example 5, manipulating K from an equation. So you have an equation for carbon solid plus 1/2 O2 aqueous, producing CO aqueous with a K1 value of 4.6 times 10 to the 23rd power. So before we even get to the questions, I just want us to see that K1, if I was going to write the expression, would be CO over O2 to the 1/2 power. Okay? So in part A, we are asked calculate K2 for this reaction. Now compare this reaction to the first one. Do you see how it's just doubled? We double it to have 2C solid, 1 oxygen, and 2 CO2. But if I'm going to write the equilibrium expression for K2, I'll write concentration of CO squared over concentration of O2, right? So this is exponentially different from K1. This would be K1 squared. Just for emphasis, I'm going to substitute K1. So we have CO over O2 to the 1/2 squared. And if we do that, if we distribute this exponent, we get CO squared and O2, so 1/2 times 2 is 1. So O2 to the first power. Okay, so that checks out. So this is K1 squared. K1 is 4.6 times 10 to the 23rd. And then we square it. Okay. So when we do that, we get 2.1 times 10 to the 47. Okay, there's A. And then B asks us to calculate K3 for CO. I'm going to erase this for a second just so I can put some emphasis on the part we're working on now. So this reaction, when we compare it to the top reaction, you see how it's just reversed. It's just reversed, right? So K3 is the concentration of O2 to the 1/2 power over the concentration of CO. So I want you to compare this with K1. See how it's just flipped? So this is equal to 1 over K1, right? Just the inverse. Or 1 over 4.6 times 10 to the 23rd, which is just a calculation there. And we get 2.2 times 10 to the minus 24. Okay, so I've shown the work here, and then I'll go on the next slide and I will review both parts A and B for you. So I went over parts A and B in detail on the previous slide. So you can go back and watch that if you want to, but just as a reminder, to calculate K2, just taking the value of K1 and squaring it, because the difference in these two reactions is we've just multiplied the top reaction by a factor of 2, which exponentially changes the value of K by that same amount. And we get 2.1 times 10 to the minus 47. In part B, we're calculating K3, where this reaction is reversed from the original reaction. So it's just the inverse. 1 over 4.6 times 10 to the 23rd is 2.2 times 10 to the negative 24th. And this has come up a few times. This dash is hard to see here sometimes because the equations are a little small. But that looks crazy. But this should be to the negative 24th power. Okay, in case it's too hard to see on your screen. Application of K. Coupling a non-favorable reaction with a small K value with one that is highly favorable with a large K value is a common way to drive a process toward product. For example, COOH3 solid is rather insoluble. You can see if we try to dissolve this solid into aqueous ions, we have a very small K value. But it can be made more soluble by coupling it with a reaction that forms a complex CONH3 3 plus aqueous. See how much more favorable this forward reaction is? So if I couple the two reactions together, what I'm left with here, COOH3 solid plus 6NH3 are our reactants, and 3OH minus and the complex CONH3 3 plus are our products, and the overall K for the two coupled reactions is 7.2 times 10 to the minus 13. And we get that value by just multiplying the first two K values. Okay, so when we combine two steps together, their overall K value is the product of the two individual K values.